Hello and welcome back, everyone. Today's going to be one of your favorite days, I'm sure. We're looking at a section, the first of two in this chapter of word problems. I know word problems aren't everyone's favorite because there isn't one way to solve all of them. The good news is, once we get the equation written, we know how to solve. Well, theoretically, we know how to solve. We've already discussed how to solve. But the setup for these should look familiar. So we've already seen the setup for these types of problems in Chapter 6. It's just in Chapter 6, the only method for solving a quadratic was by factoring. So we're going to see similar situations that we've seen before, but we may have to use new methods to solve, okay? So not one set of steps for every set of word problems, but we do have a general strategy. In general, if we're solving a word problem, we want to start by reading it, which seems silly, but sometimes we skip that. Sometimes we want to go right into a setup, and we don't really have a full understanding about what the problem is giving or asking for, okay? Whatever the question is asking for is going to be your variable in the situation. So after you read it, define your variable, and then if it's helpful, maybe organize the information that you're given. Put it into a table, highlight, underline, whatever you need. And then the hard part, obviously, is to write an equation that models that scenario. Make sure your equation models that scenario. And then the solving should be the review piece. We're going to solve using the method that's most appropriate for the problem or that you maybe prefer. So it could be square root, factoring, completing the square, quadratic formula. Okay? So let's look at our first one here, and again, hopefully this will look familiar, or sound familiar. Abby rows 10 kilometers upstream and 10 kilometers back downstream in a total of 3 hours, and the speed of the current was 5 kilometers per hour. Our job is to find Abby's speed in still water. So this is a distance, rate, time problem. Distance equals rate times time, if you remember that formula. Or depending on the setup of the situation, we might need it solved for r, where r is equal to distance divided by time, or we might need it to be solved for t, where t is equal to distance divided by rate. Okay, so in any case, I showed you a way to organize here where you can make a little table and put in the distance and the rate and the time for, in this case, Abby's 2 trips. She has 1 trip upstream, and then she has a 2nd trip back downstream, okay? So the distance, well, it's 10 kilometers up and 10 kilometers down, so a distance of 10 is going to go into both of those spots. The speed of Abby in still water is going to be our variable, right? Find Abby's speed. We don't know that. Let's call it x. So her speed, that's a rate, has got to be in both columns. I don't know her speed up, and I don't know her speed down. Now here we've got to be careful because we also have the speed of the current, right? So that's going to have to be factored into that speed or rate column. Now if you remember, what we do with that current is we add and subtract the current from the speed that we're either given or looking for. In this case, we're looking for it, so x. So if you're going upstream, you're fighting the current, you're going to be 5 kilometers per hour slower. When you're going downstream, you're going with the current, you're going to be, in this case, 5 kilometers per hour faster. So we want to subtract the 5 here because we're slower and add the 5 here because we're faster. Okay, now it tells us that the total time for both trips is 3 hours, but I don't know how much of that time was spent upstream, and I don't know how much of the time was spent downstream. So I can't put any amount of time in either one of those spots, and this is what's telling me which version of the formula to use. Since I don't have anything to go in either of those time spots, I'm going to use the t equals formula. The t equals, it says distance divided by rate. So I'm going to take the distance of 10 and divide by the rate of x minus 5. The same thing here, take the distance of 10, divide by the rate of x plus 5. And then the total of 3 hours comes in next. These 2 trips together have to make 3 hours. And that's where we're going to get our equation. So the equation becomes the trip up, 10 over x minus 5, plus the trip back down, 10 over x plus 5, purposely leaving space, has to equal a total of 3 hours. Now this doesn't look like a quadratic equation yet, But remember, we got to get rid of the fractions, and then it will turn into a quadratic. So how do we get rid of the fractions? First, let's make this a fraction. We need to get a common denominator. Once the denominators are the same, we can ignore them. So in this case, our denominator has to include one of each binomial. So this fraction is going to have to be multiplied by x plus 5. This one's going to have to be multiplied by x minus 5. And this one's going to have to be multiplied by both. And now we can see all of our denominators match. They all have an x plus 5, x minus 5, which means now we can ignore them and solve with just our numerators. So 10x plus 50 from our first one, plus another 10x minus 50 from our second numerator. And then here, it doesn't matter the order we multiply. I'd probably multiply the conjugates first, the x plus 5, x minus 5. That's going to give us an x squared minus 25, and then distribute the 3. So a 3x squared, and then a minus 75. All right, so now let's clean this up. We've got 20 x's on this side, and these cancel, so that's good. And then we still have 3x squared and minus 75 here. So now we're going to subtract over the 20x, get it equal to 0, get it in standard form. And let's see, is this guy going to factor? Are there going to be factors of 75 times 3 is 225? So 3 and 75, let's see, 5 is going to go in 45 times, 15, it's got to go in, we're racking my brain here, I don't think this is going to factor. Oh duh, I knew that. 25 is going to go in 9 times. I don't think we're going to be able to get 20 out of this. So this isn't going to factor, and that would be the difference between what we did before and what we are working on now. This doesn't factor, which means we need another way to solve. I can't square root because of that 20 that's in the middle, and I would absolutely not want to deal with completing the square in this case because I would have to divide the 3, and that would make a fraction with the 20. So I'm going to use the quadratic formula. So we're going to be plugging in 3 for A, negative 20 for B, and negative 75 for C. So I'm going to go, let me do something here. You probably didn't do this on your paper, and I am so sorry. But since I have my technology, I'm going to use it. And, okay, almost there. Hang on. Wait for it. If only you could do this on your paper, right? Just cut and paste and make things fit how you want them to. Okay, almost. Scooch a little more. Scooch. All right, looking good. Okay, so now I have all this, look at this, all this nice space to use my quadratic formula. So x is going to equal negative b, so negative 20, plus or minus the square root of b squared minus 4 times a times c, and that's all going to be divided by, excuse me, 2 times a. So x is going to equal negative makes a positive 20, plus or minus, let's figure out what we have going on under the radical here. So I have negative 20 squared minus 4 times 3, what did I do, times a negative 75. So we have 1,200 and, oh, that's a 2, Jesus, 1,300 underneath our square root. Boom, boom. Okay, and then on the bottom, 2 times 3 is going to make 6. Now, if we were looking at a situation without any context, then I would say simplify the radical to get your simplified answers. But here what we're looking for is Abby's speed. We're not going to say that she's, 20 plus or minus radical 13 over 6 kilometers per hour. So it wouldn't make sense to give an answer with the radical in it. So we're going to approximate these answers from here. Okay, this is saying that 20 plus radical 1300 over 6 is an answer, and that 20 minus radical 1300 over 6 is an answer. So I'm going to approximate those. 20 plus radical 1300 all divided by 6 was about 9.3. And then if I change the plus to a minus, then we're looking at a negative 2.7. And obviously we can't have two speeds for one Abby, and also speed can't be negative, so we're going to take the 9.3. So she's going about 9.3 kilometers per hour. So 9.3 kilometers, oh my gosh, per hour. It's hard to write on the edge of the iPad here. Okay, so there it is. I know that was super fun, right? Okay, well, we're part way there. I'm about a third of the way. All right, number 2. Again, this is one that should sound familiar. We've seen the setup on something like this before. So working together, Tanner and Joel can grade their students' projects in 2 hours. Working alone, it would take Tanner 2 hours longer than it would take Joel to grade the projects. How long would it take Joel working alone to grade the projects? So Joel, I want my highlighter. Joel working alone, that's going to be our variable here. Let's call it x. Now remember the setup here. In this case we've got Tanner plus we have Joel, and that would put them together, right? So Joel was the X factor there. We don't know how long it was going to take him to grade projects, but it said that Tanner takes 2 hours longer than Joel. So if Tanner takes 2 hours longer than Joel, for Tanner, we can put X plus 2. And then together gives us, let's see, right here. Together it says they grade the projects in 2 hours, right? That's together. So over here, we're going to go with 2. Now, if I left the equation like this, and I purposely left the plus and equal a little high there, this wouldn't make any sense. If I had 2x plus 2 on this side and 2 on this side, subtract the 2 to make a 0, and then divide, we get 0 for an answer. Would Joel take 0 hours to grade projects? No. Remember what we had to do was convert each of these amounts to a rate, and for instance, the 2 hours they take together, right? If they took 2 hours to complete these projects, or grade these projects, in one of the hours they would have done half of the job. So a 2-hour time limit is half of the job per hour, right? So to go from the amount to the rate, which is what we need in our equation, we had to flip this number over, or technically, well, technically it's reciprocate the number, but we could just put a 1 over it. So we're going to, and you could look back in your chapter 6 notes, there's more explanation there if you don't remember, but we're going to make this 1 over x plus 2, 1 over x, and 1 over 2. And now again, we don't have a quadratic equation, but if we get rid of the fractions, we will. So this time, our common denominator is going to have a 2 and an x plus 2. So this, let me just, cheat. This first fraction has the x plus 2. It's going to need to be multiplied by 2 and an x. The second one has the x, but it's going to need to be multiplied by 2 and an x plus 2. And then the last one has the 2, but not the x, or x plus 2. Okay, and now all of our denominators have a 2, an x, and an x plus 2, and once those denominators match, we can focus on our numerators. So this numerator, 1 times 2x, is 2x. Here, 1 times 2 is still going to be 2, times x is going to be 2x, times 2 is going to be 4, and then 1 times x is x, times x is x squared, and times 2 is 2x. And now if we clean this up, we've got 4x plus 4 on this side, and still an x squared plus 2x on this side. I'm going to get this in standard form. So I'm going to subtract over the 4x and 4. So I get the 0 on this side. So now I have 0 equal to x squared, 2 minus 4 is negative 2x, and then minus 4. And again, we did this before, but we had a factorable equation here. It's a little more obvious than the last one that we cannot factor. Aren't going to be any factors in -4 that make -2. And we can't square root because that -2x is in the middle. But this one I think would be a good candidate for complete the square, so that's what I'm going to put here just so you have some variety in your notes. Now, if you don't like completing the square, you can absolutely use the quadratic formula. Okay, it will still get you the answer. So if you want to go ahead and use the quadratic formula and then compare with what I got using the complete the square method, then that's fine. But just so you have some variety in your notes, I'm going to complete the square. So I'm going to leave the x squared, the -2x, and I'm going to move the -4 back to the other side to make it a +4. And then I just got to figure out what I got to add to both sides to make the left side factor. So the formula said to take half of b, so half of -2 would be -1, and then square that to make a +1. So I'm going to add one here and add one here. And then the factors of 1 that make -2 are -1 and -1. All right, factors of 1 that make -2 are -1, -1. So this is going to factor into x, it's going to factor into x minus 1, or x minus 1 squared. And on the other side, I've got a 5. And now I can square root both sides. So now I have x minus 1 equal to, don't forget your plus or minus, and then I can't simplify the square root of 5. And then I lastly need to add the 1 over. So then x is equal to +1 plus or minus radical 5. And if we had no context, we would stop there, but however, we're looking for how long it takes Joel to grade these projects. So we're going to have to put this in the calculator. 1 plus a radical 5 and 1 minus a radical 5. And we're going to get approximately, let's see, 1 plus radical 5 is about 3.2. And then 1 minus radical 5 is going to be -1.2. And he's not going to have a negative speed, so we're going to eliminate the negative option and keep the positive. So 3.2, again, that was Joel. That's how long it would take him to grade these projects. So we're going to say about 3.2 hours. And really over here we should have said about 9.3 kilometers per hour. Okay? 2 down, 1 to go. 1 to go on the back that's just broken into a couple of different parts. Okay? Getting there. All right, so these 3, A, B, and C, all pertain to this setup here. It says the distance, S. It's a good variable for distance, right? I just took this from the math lab. There's one like it with the same kind of variables, so I didn't want to try to confuse you too much. And I didn't even put S in here. Goodness. So the distance S of a falling object after t seconds is given by the function that should be S equals 4.9 t squared plus v sub 0 t, where v sub 0, this little weird thing here, it just represents an initial velocity, okay? So don't get hung up on that subscript. It's just like any other variable. So it's initial velocity. So we have a function here, which is good. We don't have to try to come up with our own equation. We have one given to us, and generally when that's the case, you're going to be given values for certain variables, and then whatever variable remains would be the one that you're going to solve for, okay? So part A, it says that a life preserver is dropped from a helicopter at an altitude of 75 meters. Approximately how long does it take for the life preserver to hit the water? So look what's happening here. And excuse me, let me back up. There are 3 variables in this, right? There's S, which was distance. There's t for seconds, and then there's v sub 0 for initial velocity. Okay, so I apologize. I gotta get some water here. Okay, so we're gonna be given values for 2 of them and have to find the third one. So a value for S, a value for t, a value for initial velocity. the 3 variables, 2 will be given. The last one is the one that we're going to have to figure out, okay? So in this part A, it says that the helicopter was at an altitude of 75 meters. That's a distance, so that means S is 75. And then it says approximately how long is it going to take. So how long is the question? That means the time is going to be the variable that we're solving for. How long is it going to take for the life preserver to reach the water? So the initial velocity, it's not clear here, but it is given. Okay, how fast is the life preserver going initially? So if it's sitting on this helicopter and it's just dropped, then it doesn't have any initial speed. Somebody's just holding it, it's not going anywhere, and then it gets dropped. So even though it's not like, said outright, the initial velocity has to be 0. So we're going to plug in all the values that we have here, leave t in. So instead of s equals 4.9 t squared plus v sub 0 t, we are having 75 go in for s, 4.9 t squared, that can stay, and then instead of v sub 0 times t, it's 0 times t, and that makes that term go away. So really just solving 75 equals 4.9 t squared. And that's not a bad one to solve. This we can use our square root method on. So we're going to divide over the 4.9. And then I'm not going to divide that just yet. I don't want to have to round 2 times. So if I put that in the calculator, it's going to give me a decimal, and then I would have to square root the decimal. I'm going to do it all at once so I don't have to round twice. Now that I'm here, to get rid of my square, I take the square root. So technically, t is going to equal plus or minus. Now let me go to my calculator. Let me go square root of 75 over 4.9. It's 3.9. 3.9 plus or minus 3.9. Now, technically, both of those are answers. Without context, we would keep them both, but time can't be negative, so we're going to keep t equals 3.9 the positive answer. We're going to say that it would take about 3.9 seconds for the life preserver to hit the water. Okay, not so bad. All right, B. Same formula now. So same 3 variables, a distance, a time, and initial velocity. So 2 will be given. We're going to figure out the one that's left over. So a coin is tossed downward with an initial velocity of 30 meters per second from an altitude of 75 meters. How long is it going to take? Approximately, how long does it take for the coin to reach the ground? So the initial velocity is 30. It's dropped from an altitude of 75 meters. That's our distance. How long is it going to take? I don't know. Time is going to stay in there as the variable. So this time we have 75 equal to 4.9 t squared plus, battery pencil, sorry, plus 30t. Good thing we're nearly done. Can't use a square root method on this guy. So 4.9 t squared plus 30t. Subtract the 75 over to make the 0, and I don't think this is going to factor. And I would even attempt it or to complete the square. So we're going to go to quadratic formula. Here's A, here's B, here's C. So x is going to equal negative 30 plus or minus the square root of 30 squared minus 4 times 4.9 times 75. And that's all going to be divided by 2 times 4.9. So we have negative 30 plus or minus. Let's clean up that mess under the radical. So we have 30 squared minus 4 times 4.9 times times, guys, you're gonna let me mess this up. This is a negative 75 in here. Negative 75. Calculator. Come on, calculator. Okay, negative 75. All right, so 2,370. And then at the bottom, 2 times 4.9 is going to be 9.8. So we're going to approximate that. Let me go up here. Obviously, negative 30 minus the radical 2300 is not going to work out. So this is going to be approximately, let's just do the positive. We've got negative 30 plus radical 2370, and that's going to all be divided by 9.8. 9.8. So we get 1.9. This is going to be about 1.9. And that represented, oh, I said x, goodness. Let me fix this while I'm here. It is x technically, but in this case, t we were solving for. So we're going to say about 1.9 seconds. Okay, last one. And feel free if you want to give it a pause and try. We're going to have some distance, some time, some initial velocity. So in this last one, approximately how far is an object going to fall in 2 seconds if thrown downward at an initial velocity of 20 meters per second from a helicopter? So how far means we're looking for the distance this time. Is it going to fall in 2 seconds with an initial velocity of 20 meters per second? So we're leaving s in there, and then we have 4.9 t, which is 2 squared, plus initial velocity 20 times t, which is 2. So this doesn't even require any solving. The variable we're looking for is already on the one side of the equation by itself. So this is literally just a calculator problem. So we have 4.9, 0.9 times 2 squared plus 20 times 2, and 59.6. So this is going to be about 59.6. This is a distance in meters. Okay, so there you have it, guys. Hopefully your homework isn't too much different, although if you run into